All right, we'll continue with question 5, which is the integral of secant fourth x to tangent cubed x dx. And we can rewrite this to be secant squared x times tangent cubed x times secant squared x dx. And we can see that those are the same. And we can rewrite this using Pythagorean identity, making this 1 plus tangent squared x times tangent cubed x times secant squared x dx. Then we can use u substitution, where u is equal to tan x and du is equal to secant squared x dx. So we can go ahead and replace the secant squared x dx and tan x. And we would get the integral from the integral of 1 plus u squared times u cubed du. And we can go ahead and FOIL, and that'd be the integral from u cubed plus u to the 5th du. And when we integrate this, we get u to the 4th over 4 plus u to the 6 over 6. And we can go ahead and rewrite this using u is equal to tan x, and we get tan of 4x over 4 plus tan of 6x over 6 plus c. That'd be the final answer for number 5. Number 6 is to integrate 1 over x cubed plus 4x. There is 2 ways of doing this, and I think I'll be able to do both. Let's start with fraction decomposition. So we can say 1, we are going to pull out this fraction, and we can say 1 over x cubed plus 4x is equal to 1 over x squared plus 4. And we can say that can be equal to a over x plus bx plus c over x squared plus 4. And if we find our common denominators, we can eliminate the denominators, and we can set this equal to 1 is equal to a times x squared plus 4 plus bx plus c times x. And we can plug in values for x so that we can go ahead and find some of our coefficients. So if we say x is equal to 0, we'd get 1 is equal to 4a, and these would become 0. So we know that a is equal to 1/4. And now we can go ahead and group together we can go ahead and FOIL, So we'll get 1 is equal to ax squared plus 4a plus bx squared plus cx. Then we can go ahead and group together our like terms. We get a plus b x squared plus cx plus 4a. And we know that a plus b has to be equal to 0, since there is a 0x squared here and a 0x. Since we know a is 1/4, that would make b equal to negative 1/4. And we can find c is equal to 0 from right there. Now, this integral would be equal to this. And when we plug in our values for a, b, and c, we can say it is equal to the integral of a is 1/4 over x, b is negative 1/4, so we can say minus 1/4 x over x squared plus 4, and since c is 0, we didn't write it, dx. We can split up this integral, and I'm going to go ahead and move it down here so we have room for the second method. This integral would be using u substitution, where u is equal to x squared plus 4, making du over 2 equal to x dx. And we can move this coefficient outside along with the negative, and this x dx would replace this, and the u would replace this. So this would be equal to negative 1/4 over 2 is 1/8 times the integral of 1 over u du. This would be equal to negative 1 over 8 natural log. Substituting back the u, we get x squared plus 4. And bringing the entire equation together, this would be 1/4 natural log of x minus 1/8 natural log of x squared plus 4 plus c. The next method we can use is actually very simple. We can factor out an x cubed. X cubed would be 1 plus 4 over x squared dx. I'll go ahead and move this over here so we have room. And we can say u is equal to 1 plus 4 over x squared, which would make du equal to negative 8x over x to the 4th dx. And we can say du over negative 8 is equal to 1 over x cubed dx. So we'll go ahead and bring out the negative 1/8, and we'd be left with the integral of 1 over u du, which is equal to negative 1 over 8 natural log of u. Substituting back in, we have 1 plus 4 over x squared plus c. Those would be the final answers. For number 7, we have to use the appropriate test to show the series 2 to the n plus 5 over 3 to the n converges. We can use the, we can compare 2n plus 5 over 3n. We can compare it to another series, and that series can be 2n over 3n. That would be the same as 2 over 3 to the power of n. And since we know this is a geometric series, this would make r is equal to 2 over 3. And we know when the absolute value of r is less than 1, the series converges. So now we know that this series that we just made up converges, and now we need to find a way to prove that this series converges using this series. We can do this by setting 2n plus 5 over 3n. We can multiply by the reciprocal of 2n over 3n, which would be 3n over 2n. And we can cancel out the 3n. I'm sorry, I forgot to mention, we'd be taking the limit as n goes to infinity of this. So we'd be left with the limit as n goes to infinity of 2n plus 5 over 2n. And if we divide both sides by 2n, we'd get the limit as n goes to infinity of 1 plus 5 over 2n, which is equal to 1 plus 0, which is equal to 1. And since that number is greater than 0, and it's finite and positive, we know that both of the functions either converges or diverges. And since we know that the series we made up converges, we can say that 2 to the n plus 5 over 3 to the n also converges. To test for absolute convergence, we could just say since the limit of n goes to infinity, 2 over 3, since that is equal to 2 over 3 and is less than 1, the limit of 2 over 3, I got this by evaluating this limit, is less than 1. We know that that is absolutely convergent. Thus, we can say the given series n goes to 1 to infinity of 2n plus 5 over 3n is absolutely convergent, and if it is absolutely convergent, it is therefore convergent, which we proved anyways by the limit comparison test. Next, we'll go over number 8, which has parts 1 and 2. We have to determine whether the following series converges absolutely, conditionally, or diverges with justification. So, let's see how these series act first. When we plug in, starting at 0, we can plug in values, and we would get 1 minus 1 over root 2 plus 1 over root 3 minus 1 over root 4 plus 1 over root 5 minus 1 over root 6. We can see this alternates, so we can use the alternating series test. And that means that in an alternating series, there is a Bn that takes away the alternatingness, which would mean we have 1 over n plus 1 square rooted. And we have to prove Bn is greater than or equal to Bn plus 1. So Bn plus 1 would be n plus 2, which would be less than or equal to 1 over n plus 1. And we can see that that is less than or equal to or greater than or equal to, depending on how you look at it. So that's the first thing we have to prove. The next thing we have to prove is that the limit as n goes to infinity of Bn, which is 1 over n plus 1 square rooted, we have to prove that this goes to 0. So if we divide the numerator and denominator by 1 over square root of n, we would get 1 over square root of n over 1 plus 1 over square root of n. And when we plug in n is equal to infinity, we would just get 0, which means that this series converges. Now, to see if it absolutely converges or just conditionally, we can take the series and set it into absolute values. And that would give us 1 over n plus 1. And we know that this does not equal the same value as this first series, because we can take values out of here and would get 1 plus 1 over root 2 plus 1 over root 3. So since we can see that there's values being subtracted and we aren't going to be subtracting values anymore, we can say that the value we get from this, which would be L, would not be equal to the value that we get from our original series. Thus, we can say the given series negative 1 to n over n plus 1 converges conditionally by the alternating series test and the absolute convergence test. The alternating series test was this one, and the absolute convergence test was this one. Next is sine of n pi over n squared. And we can actually see from seeing how what values are spat out from the series, we can tell if this converges or not. When n is equal to 1, we would get 0 over 1. When it's 2, we'd get 0 over 4. And then we'd keep getting 0, 0, 0, 0, and so on. So we can say this would eventually equal 0, which means it would converge. And for the absolute value, well, that's the same thing. 0 plus 0 plus 0 plus dot dot dot, which would be equal to 0. And since the absolute value of the series equals to the same value of the normal series, we can say the given series sine of n pi over n squared converges absolutely And we didn't use any test. We only saw this by seeing the sums go to 0. So that was questions 5 through 8, and I'll stop here.